Today I'm going to talk about sharing memory. And I have a great article here, a post on Reddit that is about sharing memory when using Goroutines in Golang. So one of Go's proverbs is don't communicate by sharing memory, share memory by communicating. It's a best practice that is used in Golang to say that when you need to communicate between Goroutines, don't use sharing memory, use share memory by communicating. And this post is about a person saying, I recently came across a piece of code that seems to violate this approach. So instead of sharing by using Goroutine, instead of sharing using channels in Goroutines, so you are using two Goroutines and you want to share data between them, you share memory by communicating by using channels to communicate, not by sharing memory, is what a proverb says. But here in the piece of code, they're using memory to share. So here we have result. Result is R, and then the result is actually going in this slice, which is called result. So here we are not using channels, we are using shared memory. So today I want to talk about when should we use sharing memory and when should we use channels. And actually, you can just scroll down to one of the answers that I really agree with. And here, one of the answers is, as you keep reading more code, you will find the proverb of using communication rather than sharing memory is largely ignored. Using channels is good, but I've also seen them get messy in large code bases. So they can get messy. It's not that easy to use always. Not sharing memory is always good if you can get away with it, but at some point you usually have to synchronize your code somewhere. Also, using channels can have a performance impact. And that's when you have to share a lot of data, you might not want to use channels, but rather share memory, because otherwise your performance would be so bad that your program is just going to take a very long time instead of using shared memory. So channels are about ownership, but when you don't really have clear ownership, protecting things with a mutex might be a better option, such as when building a shared cache. This is one example. So here this person also refers the code above. It is fine because each index is its own isolated bucket. So each index within this slice has its own, each Goroutine is going to access its own part of this slice. It's no different than if each Goroutine wrote its own variable. So this is what I want to show you today, also in code, to show you the differences between these approaches. Using a real world example. So let me get my Visual Studio Code. I'm going to create a new project. Not init shared memory. This is how I'm going to call it. I'm going to create a main.go package main. This is my main function. Here I'm going to write something. So one way that you could get exposed to these Goroutines and having to kind of merge all this data together is when you have to scrape all of data from an API endpoint. So you need to retrieve data from an API endpoint in a parallel way. So let's say you have one server and the server is going to give you JSON output, but there's like 10 pages. You can go do a GET request for every single page, or you can do, if you know already upfront how many pages you need to retrieve, do 10 requests at the same time in Goroutines, and then retrieve 10 times quicker the data, kind of. It's not going to be 10 times quicker, but if you're going to it in a serial way, you always have to wait until the first request is done, then you can do the second request. If you can do it, if you can launch it at the same time, it's going to be quicker. So to test this, we are going to start a web server. And then we're going to write a client to connect to that web server 10 times to retrieve some data. Then we're going to put it in one variable. I'm going to show you how that works. So let's start with creating a server. And I'm going to use http.serve for that. http.serve from nethttp. http.serve accepts an incoming HTTP connection, accepts incoming HTTP connections on the listener L. So that way I can first create a listener, then launch the requests, and then serve the HTTP server. Otherwise, if I would serve the HTTP server immediately, we would be in a kind of blocking state. So just to keep our code simple, I'm going to first create a listener, then do the execution of the requests, and then I'm going to start a server. So first need to then create this listener, which is a parameter, net listener. I need to pause here. So we're going to use a net package, net listen. We save this, net listen, the network string and the address. So it's going to be TCP. The address is going to be localhost 8080 or just 8080 to listen everywhere. I think localhost 8080 will probably work. Let's see. Yeah, maybe just 127.0.0.0.1. And then if there's an error, I'm going to exit the program. So now I have L, which is net listener, which I can pass here in HTTP serve, and then I can pass a handler, which is not really necessary. This will return error. HTTP serve returns an error. If the error is not nil, I'm also going to exit. Serve always returns a non-nil error. Yeah. Go run dot or go run main.go. This should start a server. Curl localhost 8080, page not found. Okay, so this seems to be working. Yeah, so if I stop my server, then I get an error, so this is all working. So if you want to open this on all ports, then you can remove the 127 IP address, but on my Mac, I then get, do you want to accept network connections? Because then you're also opening it on your public IP address. So actually, if you use 127.0.0.1, you don't get this error. It might be a little bit cleaner, because also we are only going to use it locally, so we don't want to have it exposed on our public IP address that I have on my MacBook. So now here in between, I can write some code in a coroutine. Once we hit HTTP serve, then the HTTP server will be started on this listener, and then whatever was buffered earlier, if there was a GET request, it will be handled by this HTTP server. So then we still need to have a handler handle func. So I'll say handle func. Everything from slash goes to my index function, index handler, and then I can make my index handler. My index handler needs to be of response writer and requests. So this is my writer, this is my request, save. And now I can write something. I want to write some random data. So I can use the math random for that or the crypto random for that. Math is pseudo random, so it's always better to use the crypto version. There's a function, I never know it by heart, but I'm just gonna copy paste it from here. Rand int rand reader is the argument, and the maximum is this big int right here. That gives you a big integer with a maximum of 1000. Rand is of the crypto.rand, so it's a cryptographically secure random number generator. So I try to avoid always the math random, just always make sure that you have good random numbers in case that you need to generate passwords or something. That's always done in a secure way. If there's an error, what do we do if there's an error? Log fatal rand generator random generator error. Now we still need to convert this into a string. So n big is a big integer, which we can convert to an int64, which we can then convert with string convert to an integer. We can use format int for that. Format int. What does it accept? Format int returns a string representation of I in the given base. So for int64, it is base 10. So these are string, and this we can write with our write function. So the response writer has a write function. We write a string. We have to still convert to bytes. Maybe I could have converted the int straight away to bytes instead of a string. Maybe that's one conversion too much, but here we don't really want to be super performant. These are really micro optimizations that we could do. Converting first to string and byte is fine for our use case right now. Go run. Let's have a look with curl, localhost 8080. Okay, we get a random number. So if we would write a loop, and our loop would do get requests, and it takes some time to get an answer. Let's say that it takes 5 seconds to get an answer. Then I need to refresh this. Then you see it will take 5 seconds for every request. So if you have to do this 10 times, it will take 5 seconds every time to finish this request. So requests like this, and often it's like you have like page equals 1, and then you need to wait for requests, and then page equals 2, you need to wait for requests. You can definitely speed this up by doing the requests at the same time. So if we do this in just a Linux command, we can run this in the background like this. So now we are running in this background. And now if you wait 5 seconds, we will then kind of see the output. You see the output is now coming. You see, so the output now comes much quicker than when you would run it separately. First, the first get, then the second get, then the third get, and so on. So this is exactly say what we want to achieve here. We want to make a loop of 10 requests in parallel using Goroutines, and we want to save the result. And yeah, indeed, you could use channels to get all this data together, but you can also use shared memory. There's nothing wrong with using shared memory, and I will show you how to do that. So first we need to make a Goroutine. So we can say go func, and then we need to call the func right here. So this will run 10 times a function. So let's remove this screen here. Let's print something, test, and then how many for loop, how many times we are looping this. So here you see it is actually run. It actually run in parallel, so we have 10 Go routines running in parallel. I have multiple CPUs in my machine, so one CPU could potentially take one Go routine to have it executed. Potentially. There's a whole discussion about also that Go routines is not necessarily parallel if it's on a single CPU, because if it's a single CPU, then you give some CPU time to your first Go routine, but then you stop, then you give some CPU time to your second routine. So it's not really at the same time that it happens. It all depends on how many CPUs that you have. It's just to run things in parallel. It's not automatically going to be quicker. But in our use case, because we have this time sleep here, which is just artificially making this slower, retrieving the random numbers, you will see that it's actually quicker to do it in parallel than by not having coroutines. So this is the for loop. The for loop works. So what are we going to do? We're going to do an HTTP get of localhost 80. HTTP get gives us a response and error. So here we have a response and error. If there's an error, we're just going to exit. If there is a response, then we're going to read the response. So we have body is IO read. So we're going to read all from rest body. So when I'm writing this code, I often just go to some examples because I often cannot remember all these basic things. So I just copy paste from my old code. IO read all is a function to read everything from this Rust body. Rust body has an interface that has reads, I believe. So that should all work. So IO, I just saved it, but it doesn't seem that IO has been added. So I'm just adding it manually. Okay, that works. So let's just print the body for now. What is the body? So this is a byte, but then we say we print it as a string. We'll go run. So you see it has to wait these 5 seconds. Maybe, let's say, start Go routine and then the index so we can see what's happening. So we start all our Go routines. Now we need to wait 5 seconds. And now we get all the output. So now you want to store all this information in a variable. So we could use channels, but if your body is very big, you will see that the channels are going to get slow. If you're retrieving from your endpoint a megabyte of information, a couple of megabytes, a gigabyte, you will see that it starts getting slower. Especially when you then have to also serialize it or deserialize it. Maybe it's in JSON. You need to put it in your own type. So instead of putting all this information on a channel, I can have something like result, and my result is a string slice that I'm going to use. How long is this going to be? I'm going to start with 10. And then I'm going to say results index is my body. String body, because it needs to be string. Now, something funny. Let's say I want to read it. Let's say I want to read here results. It's going to execute this. This is going to do the HTTP call. I'm going to wait 5 seconds. But then Golang is going to continue, and then it's going to print my output. So what am I going to get here? An empty slice, because these Goroutines didn't have a time yet to put the information here in this result. So let's test that. Go run. I have this empty slice here because it only started it, but we still have to wait 5 seconds to get our data. So we don't see anything here in our result. So then we can actually use something interesting called waiting groups. So we can say something like, we need a variable. I'm going to call it WG sync wait group. So this is from the sync package right here. Sync package has a wait group. A wait group waits for a collection of Goroutines to finish. So what I'm going to do is, I'm going to say, and we only have a few functions here. So I have add, done, and wait. So I have add a delta. So I'm going to say I'm going to add this Goroutine. So one Goroutine. Every time I make the loop, I'm going to add one Goroutine. I could also add 10 of them, but it's nicer to have it just in this for loop. So I'm going to add, every time I'm executing a Goroutine, I'm going to say we have one more Goroutine. And here, when I store the result, I'm going to say this Goroutine is done. So it says decrement the wait group counter by 1. So here I'm increasing by 1, here I'm decreasing by 1. So as long as my Goroutines are running, I don't want to print anything. But at some point I have to wait. So here I have my wait function. While I'm waiting, I'm going to wait here until my counter is 0. So here I have +1, +1, +1, +1 until it's 10. And once it's done after 5 seconds, it's going to be done. -1, -1, -1, -1. Wait is going to wait until it's 0. Then I'm going to show the result. So now I'm waiting. Oh, wait, but there's still an issue. If I wait here, I will never reach my serve. So it's never going to start my HP server. So this should also be in Goroutine. Otherwise, we are not continuing with our program, with our main program. So this is going to be a separate Goroutine where we're going to wait so that we hit this serve. So now I'm waiting. And then now I have my data. So this works because every Goroutine writes to its own index. When will this not work? If my Goroutine starts writing to other indexes, because then you're mixing your result. So the reason why they invented channels is that it's a better way to exchange information. It's less prone to errors, like if you have shared memory, one goroutine could write accidentally to the variables of the other goroutine. Like I could accidentally write always to 0, and then now all my results will go in the first element, and then I lose all my other data. And you might not notice that in your code. So you get data corruption without doing something wrong. It's the code is still kind of valid. It compiles, it runs, but then at runtime, you lose your data. So you have to be very careful here. Something else that wouldn't work is if you change this variable. So if you say result equals append result string body, you might think, well, I'm just appending something to the string. Why wouldn't that work? And I need to make an empty string. So let's say we make a string slice of 0, but with a capacity of 10. Go run. It is the interesting part because it works, but actually it doesn't work. Because here we changed the variable. So it might work, but not always. And there's actually a flag in Golang to check on this. Is there a race condition? So a race condition, if we use this race condition, we compile it with this race condition, it's not on by default because it takes more CPU to figure out whether you have a race condition. But here you can already see it. We have a data race. Because we are changing this variable in our goroutine, we are doing something wrong. We have a race condition. We are appending something to result, which means that we are actually going to change this variable. It's not going to be the same variable anymore. It's going to be a different variable. But then the other goroutine could write to the previous variable, the previous slide. So let's say result has a reference pointer to address 1. So now this slice is in address 1. So now we execute. And then let's say that the first goroutine sees, okay, we still have capacity. We're going to write in this slice in address 1. So goroutine 1 writes at address 1, and it writes string 1 to 3. But then the another goroutine could decide, I'm going to do something else. I'm going to do goroutine 2 is going to say, I'm going to first create a new slice, and I'm going to put it at address 2. And I'm going to say it's going to be 1 to 3, 1 2 3 4. Then goroutine 3 didn't see yet that the address has changed. So it's going to say, I'm going to, at address 1, I'm going to add 2 3 4 5 6 to this slice at address 1. And now your slice is at address 2 with 1 2 3 1 2 3 4, and you kind of lost the data of goroutine 3 because the goroutine 3 still wrote to the address of the previous variable. And this is what this race flag detects. There's a race condition that can happen. So let's have a look. If we don't use append, is there a race condition? Is there a race condition? If we use the index, let's first see if it executes. And I'm going to remove maybe the time sleep so we don't have to wait 5 seconds every time. So, okay, here's my random data. Now I'm going to add the raise condition, the raise parameter. There's no raise. There's no warning, right? Because there is no raise condition. We are never changing this result variable. We are just saying that at this index, which is another variable, we are going to add the body. So this is perfectly possible to do using shared memory, although it's not always recommended as best practice. A lot of people are using this in their code because it's more efficient, it's more performant than using channels. It also might make your code much cleaner because you don't have to use channels. So there's definitely a difference, something that you should think of, that channels is not the only way to communicate between Goroutines. So that's it. I think it was useful to show how this can work, and that the proverbs are definitely there to help you and are best practices, but there are cases where if you need the performance gains of shared memory, for example, because you're downloading a lot of data during your GET requests, there are ways that there are situations where you just have to use shared memory and not channels. Leave me a comment and tell me what you think.